Hi and welcome to this video. In this video we will find the wave function of a particle inside a infinite square well. Well, what does an infinite square well mean? It means that there's a potential of the following form. Namely, it is 0 inside a well with a width a, and it is infinite everywhere else. We can also draw this and it will look as following, where you have your potential on the y-axis and your position on the x-axis. This is position A. It will look like this. It will just be an infinite square well. So how do we find the wave function psi? Of course, we know that we have to use the Schrodinger equation, which is given as follows. It is equal to 2m over h bar squared times the potential as a function of position minus the energy times psi. Of course, if we are inside the square well, we see that the magnitude of our potential is 0. Therefore, this is 0. So we are only left with the following differential equation. Minus 2m over h bar squared times e psi, where the minus comes from the fact that we have it all here already. Now, normally it is easier to define a value of kappa squared psi, whereby we define kappa squared as this is 2m, sorry, a minus should be there, 2m e divided by h bar squared. So the normal kappa is the square root of this. Well, this is a differential equation which you see very often in physics. So, and we know that the general solution to this is given as a combination of sines and cosines. So it will look like this. The following property that we will use is continuity. Namely, we know that the wave function has to be continuous, which implies that the wave function at the position 0 is equal to the wave function at the position a, which is equal to 0. Now, if we fill this in, we get that psi of 0 is equal to a times the cosine of 0 plus b times the sine of 0 is 0. But of course we know that this is also 0, and this is just simply 1, which means that a is equal to 0, and therefore we are only left with the sign in our general solution. Now we use the fact that it is equal at position a to 0, which means that b times the sine of kappa a is 0. Well, now we have to solve this, but of course this is 0 if the sine of 0, if the sine of kappa a is 0. Well, of course b can also be 0, but that is the boring case, because then you just have psi is 0. So we want to find a non-trivial solution only. Now, the sine of kappa a is 0, of course, if kappa a is 0 or plus minus pi or plus minus 2 pi and so on. We can also write this down as kappa a is equal to n times pi. Well, and it's now an integer, and it can be either positive or negative. This means that kappa is equal to n pi divided by a. But of course we know what kappa is, namely it is equal to the square root of 2me divided by h bar squared. So this should then also be equal to n pi a, and this of course follows from how we define kappa. Now we can solve this for the energy, namely by squaring both sides, which of course gives us 2me divided by h bar squared is equal to n squared pi squared divided by a squared. So E is equal to n squared pi squared h bar squared divided by 2m a squared. Now this is just, so this is what the energy of the particle or the wave should be. This is of course different from classical physics, because there every energy is allowed. So this is really the quantum physics in our problem. We see that we can only have a wave function with an energy quantized, namely En should be equal to pi squared h bar squared over 2m a squared, which is of course, and not of course, but this is really the quantum physics in the problem. Now, since we still have to calculate the wave function, we have to find the integration constant. Now, how can we do this? We can use the fact that the wave function is properly normalized. That implies that if we integrate the wave function squared over x, it should be equal to 1. So, since we only use the wave function inside, we integrate from 0 to a, should be integrated over x, and this should be equal to 1. This integral can be solved by using that sine squared is equal to 1 minus cosine squared, which can be evaluated to give a over 2 times the b squared, and this is 1. Therefore, b squared is equal to 2 over a, and so b, so this is equal to b. And then if we plug this back into the wave equation again, we find that the wave equation is equal to the square root of 2 over a times the sine of n pi over a times x.